Good morning, Zachary. We'll get started here shortly. Let's give folk a chance to get here. Thanks for your patience. All right, good morning, everybody. Thanks for joining in. So let me go ahead and share my screen. If you're seeing the course homepage, please let me know.
Yes, ma'am.
Thank you. All right, so on Tuesday, oh, sorry. Bear with me just for a second. I got to go back and re-log in. I always forget that if I don't switch over to Nunez, the left menu is not going to cooperate with me. So there you go. All right. So just as a reminder, this session is being recorded. I will get it posted. I did get the other videos captioned. I just haven't taken a moment to post them in the announcements, but I'll get that done here later on today. Sorry for the delay with getting that out to you. All right, so here we are. Newton's laws overview this week. I did go back, heard the class discussion, and I put an announcement that I updated everything so that, You only have the Newton's law stuff on your plate this week so that you can focus on your midterms. I recall y'all telling me that you're doing midterms now, even though you're finished with mine, but you're doing midterms for other classes. So, you know, you have a lighter load because you only have a discussion that's due. Well, actually, problem set 5, which is on 2D motion, and Newton's laws discussion, which is much lighter load than what you would have had if we had included gravitation, right?
Yes, thank you for that. I appreciate
Oh.
it. It definitely helped me out a lot.
Yeah, no problem. I get it. You know, I'm swamped myself with the grading and I've got new classes starting, and you know, so I really do appreciate the fact that you guys are just as busy as I am. And you know, I didn't mind making the adjustments to take the load off a bit. So let's take a look at the items that you have due. And then we'll finish up our look at 2D motion. I mean, excuse me, at Newton's laws. I'm mixing you up with the other class. All right. So problem set 5. Basically, you're using a simulator to look at projectiles. And it's actually the same simulator that I think we took a look at in class the other day. Am I right?
Yes, ma'am.
Okay. So you're familiar with the actual simulator. Let's just take a look at what you're going to be using it for in problem set 5. So you're going to be changing the values in the simulator 5 different times. So these numbers that you can key in, you want to change them 5 times and run it. And then, but don't change the mass, leave it at 1 kilogram, okay? Because if you do, then that's gonna bring into play forces and energy, and we're not ready for that. So keep the mass at 1 kilogram. And if I were you, I would just leave the acceleration at 9.8 meters per second squared, because I mean, there's nothing wrong with keeping that fixed. If you want to change it, feel free. But the only values that you have to change are the height, the speed, and the angle. If you want to leave the mass and the gravity fixed, that's fine. Okay. If you know, you shouldn't have any trouble with this simulator because it's HTML5. It should open readily in the browser. But I did make available to you some screenshots in the event you had trouble with it. And that used to happen in the past, but I don't see that happening now. But if it does, you have access to the screenshots there, okay? And those screenshots are basically, I ran the simulator for you, okay? I would prefer you do it yourself because that's what, you know, you'll get more out of it if you do it yourself. But if you run into trouble and you want to use mine, that's fine. You just have to be mindful. If you use my screenshots, you still have to turn those in, right? So you change in the simulator 5 times, you run it, you know, print out the screens, okay? And then you use those printouts to help you answer the following 5 questions, okay? And you're answering the questions for each run, okay? So like every time you put a new set of numbers in, answer these 5 questions, okay? Does that make sense to you with problem set 5?
Yes, ma'am.
If you're working and you run into questions, don't hesitate to reach out to me. I'll be, you know, I'm checking email and what have you regularly, so don't hesitate. The Newton's laws discussion, again, I think I talked about that on Tuesday. You got to answer these questions, and then you're supposed to be having a discussion with your classmates about what they've posted. And then your first bonus. I hadn't talked about this at all, right? So this is the first bonus that you'll have in this class. You'll actually have 3 before it's over. And the first bonus is on circular motion because we've already covered that. And it's worth 10 points toward the midterm. So if you do this bonus, I'll go back and add the 10 points to your midterm score. I still have to finish scoring the midterms. I've scored about half of them already. But you know, I'll add the bonus points in. And so the bonus points won't be there when I score it your midterm this week, but I'll just go back into it and add the points once you turn this in, if you turn it in. Okay.
So, but also, we also got another 10 points as we did the midterm study guide, correct? And sent it
That
to you.
that's correct. And also, if
Okay.
you looked at, if you recall week one, I don't, well, no, maybe not for you guys. That's not for you guys. I apologize. But yeah, so 20 bonus points on the table, right?
Okay. Thank
Yeah.
you.
No problem. So what you have to do is you have to go to this website. This website deals with the International Space Station. I think by now you guys probably know that, you know, I'm kind of, I have an affinity for satellite motion because, you know, I'm fascinated by the fact that there are people living out there for extended periods of time. So I wanted you to have opportunity to come out here to the International Space Station website, utilize this website to answer these two questions. So you go to the website and then you're going to answer these two questions. It says, write a brief description of something that you learned about the International Space Station from the website, and then use their locator tool to determine when the International Space Station, that's what ISS stands for, right? When it will pass over your hometown or the closest city to you, right? If you live in a small town, you probably won't get feedback. But then if you just go to the closest city to you, like, you know, if you live in, you know, like, so most of you guys are out near the Chalmette area. So I don't know if you can get information on Chalmette, but New Orleans for sure, right? That's the kind of thing that I mean, okay? So there's a locator tool on here. You see, find sighting opportunities. So you put in your town and it'll give you that information, right? And so you write that up for me and turn in your answers to both of these, and it's worth 10 bonus points. Any questions about that?
Oh, ma'am, that sounds great.
Cool. All right. So those are the things you have to get to me by Saturday. So on Tuesday, we went through all of my slides. What I told you was that on Tuesday, what I wanted to do was to come out to what I wanted to. No, I was right. I'm looking. My brain's frying right now. I'm going into my extra notes, the extra resources that I provide for you. Okay. So if you click on that, there's a folder that has, well, it wants to be slow this morning. Come on. Well, let's hope that Google isn't frozen this morning, but there we go. All right. So you see here, if you have not been utilizing this stuff, you're really missing out on some great tools, because in each of these folders is some extra resources and materials that I compiled over the years that I like sharing with students, but I don't want it to be actual part of the course because of some accessibility requirements that many of these items don't meet certain accessibility requirements, but it's still good information, right? So there's a folder on Newton's laws. And I mean, I've kind of done, you know, these are some really great extra notes to deal with Newton's laws. But what I want to do is, I want to go into this force and acceleration packet with you today, okay? And in this packet, there are some problems that are being solved dealing with Newton's second law. Honestly and truthfully, Newton's first law is all about the forces being balanced. So if the forces are balanced, you don't have any acceleration. okay? So the real problem solving for this type of course comes in when we use a simplified version of Newton's second law to solve some problems, all right? And so we'll take a look, kind of review Newton's second law to make sure that we're all on the same page in terms of, what is Newton's second law? Because you need to understand that if you're going to solve problems with it. And then we'll look at a couple of different types of forces. We'll talk a little bit more about gravity and air resistance, and finally some calculations that use Newton's second law. And the sample problems that you see solved here are the kinds of sample problems that I expect you to solve, okay? So if you remember Newton's second law from the other day, from Tuesday, we looked at the formula F equals ma. And what this formula allows us to do is to find the amount of acceleration if we know the amount of net force and the mass, remember inertia, the mass of the object. And what Newton's second law is saying is that the acceleration is directly proportional to the net force. More net force, more acceleration. You can kind of think of it in a simplified way. If you push harder on the same object, it's going to accelerate more. But Newton's second law also says that the acceleration is inversely proportional to the mass, okay? So more mass, less acceleration. So if you keep pushing with the same amount of force and the object gets bigger, you're gonna have less acceleration, okay? So what Newton's second law allows us to do is to, quantitatively determine the force, mass, and acceleration for an object, okay? And so we can express that F equals ma, that relationship in the formula F equals ma. Now that is definitely a simplified version of Newton's second law. Newton's second law is actually a whole lot more complicated than that, and even there's a calculus version of it. But we stick to this F equals ma version because it's simple enough to understand at this level, and we're really just trying to solve some simple type problems. So you can see in the square, we rewrote the formula utilizing A, right? Because as I said, that's the whole goal here, right? Newton's first law, A is 0, so there's nothing to figure out. But Newton's second law, we can get A by taking F divided by M. And then written this way, you can clearly see if F gets bigger, A gets bigger. If M gets bigger, A gets smaller, right? And now here's my famous problem-solving pyramid, where I took the formula and I put it in the pyramid. So you don't have to know how to solve an equation. You only have to multiply or divide, depending on what you're looking for, okay? So the formula F equals ma can be put into that pyramid. And recall, we have to always be mindful of units. So you have a new unit here now. The unit for force is the Newton. We use the capital letter N in honor of Isaac Newton. So remember, I told you at the beginning of the course, when we first started coming across all these different properties, all these different things that we can measure, all these different things we can solve for. Told you, get yourself a big index card and write down each property and write down the SI unit that goes with it. So when you're problem solving, you know whether you're getting the right value or not, the right unit or not. I will be honest with you, on the midterm exam, over and over again, students mess up units. So it does help to have that in front of you as a check to know, did I get the right SI unit, okay? So in this formula, F has the unit newtons, M has the unit kilograms, and A has the unit meters per second squared. Meters per second squared for acceleration gets butchered on a regular basis in this course. Please, 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 acceleration is meters per second squared, not meters per second, not meter second, meters per second squared, okay? So you gotta keep that straight. And you can see this little relationship here. 1 Newton equals 1 kilogram times 1 meter per second squared. So what this is telling you, if you take a kilogram and you take a meter per second squared and you squish them together, out pops a Newton. Or if you take a Newton and you crack it open, you get a kilogram and a meter per second squared, right? So that little relationship tells you how to make a Newton or break a Newton, which is extremely important when you're solving problems. So gravity. So as I mentioned on Tuesday, up to now, we've been really focusing on gravity as you know, an accelerator, the 9.8 meters per second squared down, right? But gravity truly can be looked at as a force. It's one of the 4 fundamental forces. And so it's the force of attraction between any 2 objects in the universe. So if you pick any 2 objects in the universe, there's a force of attraction between them, meaning they're pulling each other toward each other, right? And we call that force gravity. Now, we're not going to get into any of the nitty-gritty details beyond that, because I just want you to be thinking we can approach gravity from 2 perspectives: the acceleration it produces or the force that it produces. And when we look at it from a force perspective, this is where we come in with weight. So weight, the weight of an object is the force of gravity on that object. And that's an important force because think about it. Any object has mass and takes up space, has weight, okay? So remember, weight is in newtons because it's a force, mass is in kilograms, and G is the acceleration due to gravity, and we know acceleration has meters per second squared, okay? So if you want to find the weight of an object, you take its mass and you multiply it times whatever the gravitational acceleration is. If you're on Earth, that's 9.8 meters per second squared. If you go to the moon, it's 1.7 meters per second squared. Mars, 3.75 meters per second squared. You know, so wherever you're, whatever, you know, planet, moon, whatever you're on, you multiply the mass times the gravitational acceleration at that location, okay? And so this highlights something important that I talked about on Tuesday. Mass is an intrinsic property, so it doesn't change. Your mass is always the same, okay? So whether you're on the moon, on the Earth, on Mars, or Jupiter, or anywhere else, your mass is the same. And I always have the student that says, yeah, but what if I get burned to a crisp by, a sun, or, blowed up in a supernova? We're not talking about that, right? We're talking about you being you. Your mass is going to be the same no matter where you go, okay? But it's your weight that will be changing. Why? Because as the acceleration due to gravity changes, your weight will change, okay? There's a dependence there, right? So that's important to remember. I always like this little visual. It says, would you weigh more on Earth or Jupiter? And of course, just because of you look at like, okay, I think it's Jupiter because it looks bigger. Yeah, but you have to think about the fact that Jupiter has a greater mass than the Earth, which means then it has more gravity than the Earth, which means then your weight will be greater on Jupiter than the Earth, okay? And we're going to go deeper into that whole gravity piece next week. That's why that gravitation business that I adjusted on the schedule, we're actually going to be dealing with that next week, okay? So let's talk about this thing you already know a good deal about, and that's the acceleration due to gravity. So we always talk about no air resistance. No air resistance, everything's going to fall with the same acceleration, okay? Please do not mix up velocity, speed with acceleration. They're not the same, okay? So if an object is falling just with gravity, no air resistance, then that object is going to have an acceleration 9.8 meters per second squared on Earth. It doesn't matter whether it's an elephant or a peanut, they got a feather, but I like elephant and peanuts, right? Okay, so no air resistance, the elephant and the peanut are gonna fall with the same acceleration. Okay, I didn't say same velocity, I didn't say same speed, I said same acceleration, okay? You could figure out though, that if the acceleration is the same, then ultimately their velocities will be the same at any given time, okay? But you want to key in on the fact that they're falling with the same gravitational acceleration, all right? But you know, the question is then why? Why is this elephant and this peanut gonna fall with the same acceleration? What's going on there? Well, of course, we don't have any air resistance, but let's look at it from a thought, you know, a kind of thought process, right? So I think most of you would agree that the elephant has more weight than the peanut. You would probably agree, hopefully, that the elephant has more mass than the peanut. When you take the elephant's weight divided by the elephant's mass, you get 9.8 meters per second squared. Okay, let's go over to the peanut, or the feather as they're calling it. You agree that the feather or the peanut has less weight than the elephant. Also, the peanut has less mass than the elephant. But when you take the peanut's weight divided by the peanut's mass, you still get 9.8 meters per second squared. So it's the ratio of weight to mass that's constant when there's no acceleration, okay? It's just like saying 20 divided by 5 is 4, 4 divided by 1 is 4. It's the ratio that always comes up the same when there's no air resistance and an object is falling. We call that free fall, right? But what if we want to include air resistance? Of course, as I told you many times in this class, we're not nearly at a point where we can do anything mathematically where air resistance is concerned. So, you know, it's like a concept that we want to understand. What happens when you include air resistance, okay? So there are different names for air resistance, some fluid friction, especially for those folk who are in P-Tech and you have to take fluid mechanics. You learn about that whole idea of fluid friction or drag. And you'll look at some of the factors that it affect air resistance, or what, you know, that air resistance depends on, okay? And that's speed. The faster you go, the more air resistance you generate. Surface area. So if you want to test that, you know, like when you're a kid and you stuck your hand out the window of the car, if you held your hand with your palm facing the wind, you could feel it pushing, as opposed to if you put your hand flat, right? Because that's a surface area thing. More surface area, more air resistance. And then shape. It's the reason we build cars or rockets, and, you know, to have a cone shape that makes them more aerodynamic and means they generate less air resistance. It's also why SUVs burn a whole lot more gas, because typically they're box shaped, so they have a, you know, that they have a larger surface area and they catch more air resistance, which means you got to use more fuel, which costs a lot more right now to go the same speed, right? And then the density of the fluid, the density of the air impacts the amount of air resistance. You know, resistance, you've heard cold air sinks, hot air rises. That all impacts the amount of air resistance, okay? And so, see, before we couldn't talk about air resistance because air resistance is a force. And if we don't have the tools to talk about forces, then, you know, if you're looking at things from a kinematics perspective, you can't talk about air resistance because that's a force. But now that we're doing dynamics, we can include forces like air resistance. And since we can include those types of forces, we can look at a phenomenon now called terminal velocity. So we couldn't talk about that before, because to talk about terminal velocity, you need to talk about forces, all right? And so terminal velocity is like the maximum velocity for a falling object, okay? So it's the biggest velocity that it can have while it's falling. So when do objects reach terminal velocity? Well, that's when the force of gravity pulling down on the object, we know that as the object's weight, is equal to the air resistance force pulling up on the object. Like when they pop a parachute as shown in the picture, you know, the parachute is going to generate air resistance, and that's going to be pulling opposite to the force of gravity pulling down on the object. When those two forces are balanced, remember Newton's first law says what? When all the forces balance out, cancel out, no net force, you can't accelerate. So if you can't accelerate, you have to be falling with the same constant velocity. And we call that terminal velocity, okay? So you see, this is a real example of Newton's first law, this idea of terminal velocity. And so that's what's being illustrated here in the picture. The person is falling out of the helicopter. But when they first start falling, they aren't going to be at terminal velocity. So what happens is as the person falls, and you know this from your own experience in dealing with free fall already, as an object falls, as this person falls, they're going to go faster and faster because gravity is pulling on them, right? Accelerating them downward. Acceleration means what? Your speed increases, right? So as their speed increases, so does the air resistance, because I just told you that more speed, more air resistance. So as the person falls and goes faster and faster and faster, they generate more air resistance. Well, eventually it gets to the point where the air resistance is just as big as the force of gravity on them. And when those two things are equal, those two forces are equal, then the person falling will reach terminal velocity. You know, the only hope is that they have enough time left in their fall that they won't immediately hit the ground, right? Because that's when like injuries can happen, right? Falling at terminal velocity, but you reach terminal velocity just as you're hitting the ground. That's not going to be good. So if you include air resistance, then elephants do fall faster than peanuts, as you probably intuitively expected, right? I mean, your intuition tells you that an elephant is going to fall faster than a peanut, but that's because you're used to including air resistance in your thought process, okay? So if we put air resistance in, heavier objects fall faster, but the question is, why do they fall faster? Well, the elephant has more weight. So because the elephant has more weight, that means they have a bigger gravity force pulling down on them, right? Well, if you have a bigger gravity force, you need a bigger air resistance to balance that out. If you need a bigger air resistance, then you need a bigger speed, okay? So more weight, more air resistance, more speed. And that's why in the real world, elephants fall faster than peanuts. All right, so the last few slides here are about some calculations. Remember the kinds of things that you should be able to do with Newton's second law. So we'll take a look at those sample problems. So it says, what force would be required to accelerate a 40-kilogram mass by 4 meters per second squared? So they gave you the mass and the acceleration. They want the force. So the way the problem solving pyramid works is whatever you're looking for, you cover it up. That's my smiley face. It tells me that I have to multiply the mass and the acceleration. Why? Because they're right next to each other. Okay. So that means I have to take 40 kilograms and multiply it by 4 meters per second squared. That becomes 160 newtons. If you solve this and you tell me 160 kilogram meters per second squared, I'm going to mark it wrong. It means that you don't understand that when you put a kilogram and a meter per second squared together, you get a newton. Okay, so please be careful with these units. Well, let me back up. I do apologize. What questions do you have about this first example utilizing Newton's second law? Okay.
I don't have any.
Okay, thank you. So let's look at another calculation. It says a 40 kilogram shot put is thrown with 30 newtons of force. What is its acceleration? So in this case, they gave you the mass, they gave you the force, they want the acceleration. So in the problem solving pyramid, you cover up the acceleration, that's the smiley face, and it tells me I have to take the force and divide by the mass. I know that because force is on top and mass is on the bottom, so I have to divide, okay? So that's 30 newtons divided by 4 kilograms, okay? Now the 30 divided by 4, that's easy enough to do in your calculator to get 7.5. But pay attention to the unit here. They took a newton and divided by a kilogram, and the result is a meter per second squared. Why? Because remember, if you crack open a newton, what do you have? You have a kilogram and a meter per second squared. That means you have a kilogram on the top and a kilogram on the bottom that cancel each other out. And that leaves you with meters per second squared, okay? Any questions on this problem?
No, ma'am, I understand it.
Good, good, good. Thanks for the feedback. All right, so this last one, I want to pay attention closely to this last one because it's one that sometimes gives students a little bit difficulty. So it says here, Mrs. J weighs 557 newtons. Now I know typically when you're used to dealing with weight, it's probably pounds, right? But remember, we're doing SI units, so we express weight in the form of newtons. And they want to know, what is Miss J's mass, right? What is her mass? Well, see, this is where some students have a disconnect. They don't take into account that weight is actually a force. And so what they're giving you there is F. Okay, and that F in this case is the weight, 557 newtons. They want you to find Miss J's mass. But in the back of a lot of students' mind, they're thinking, well, how can I find the mass if I don't know the acceleration? They gave me the weight, I see newtons there. They want me to find M, but A is missing. But you have to remember that anytime you're dealing with weight, they gave you the acceleration because you're using G. In this case, since we're on Earth, 9.8 meters per second squared, okay? So anytime you're dealing with the force weight, then the acceleration is automatically the acceleration due to gravity, okay? So now you do know F and you do know A. To get M, you simply divide F by A. If you look at the pyramid, That's 557 newtons divided by 9.8 meters per second squared. Okay, so you can do the number part in your handy dandy calculator. Now you have newtons divided by meters per second squared. And when you do that, you get a kilogram. Because remember, if you crack open a newton, you have a kilogram times a meter per second squared. That means you have meters per second squared in the numerator and denominator, which are going to cancel out and leave you with the kilograms. Okay. So when you're solving problems with Newton's second law, one of the major things that I look for is, are you dealing with the units properly? Okay. So just be thoughtful about that when you're solving problems, to pay attention to the detail of getting the units correct. All right. Any questions about this last example?
No, ma'am. I
Okay.
actually understand. That's a lot better than all the other ones that we went over before this. This like makes a lot more sense to me.
Oh, so you like this packet of notes that I'm using? Is that what you mean?
Yes.
Yes, that's why I made it available to you, because I like it because it's a little bit cleaner. It's, crisper in terms of what it is that you're trying to get at. But until I can take every single slide and every single picture and do some things with it that'll make it accessible to things like screen readers and so on and so forth, I can't officially put it in the course. I can share it with you, as just common knowledge, and you can use it as you want to, but I can't use it as my official notes. Go figure, right? But I just kind of told them, I'm not throwing these notes away. They're really good. Over time, students have found them really useful. So I'm going to make them available, and students can use them if they want to. All right. This last thing is a cool little concept test to see if you got your thinking caps on. So it says, is the following statement true or false? An astronaut has less mass on the moon since the moon exerts a weaker gravitational force. Well, that's false because of a couple of things, right? Mass doesn't change as you move from place to place, okay? Because the mass doesn't depend on gravity, okay? But your weight does. So the astronaut has less weight on the moon, but that's not because of the astronaut's mass being different on the moon. Okay.
Yes. Weren't you talking about that in the last lecture on Tuesday?
Yes, I was talking about the
Related
idea.
to something just like that.
Yes, I was on Tuesday. I talked about the idea that your mass is an intrinsic, meaning internal property that doesn't change as you move around. It's a location independent. And that also has to do with the fact that mass is a scalar. If you remember the lesson on vectors and scalars, some properties that you measure are vectors and some are scalars. Mass happens to be a scalar property, meaning it's location independent. So as you move about the universe, your mass doesn't change. And I'm not talking about if you lose weight, get burned up, get zapped by a Dormammu, that kind of thing. No. Okay. For y'all that don't know, that was a Dr. Strange reference. But anyway, but as you move around the universe, your weight will change because the gravity will be different in different places. And that also goes to the fact that gravity is a force, meaning it's directional. Okay. So I hope that helps to give you a clear picture about that in your mind. Okay, so I don't have anything else that I wanted to share with you today, but I am open to any questions that you might have at this point about anything we've covered this week or anything that you've got to get done this week.
I have a question. Are we gonna have, we have lab after this, correct? At 11:30, we're gonna have lab class.
Yes, we did meet on Tuesday, am I right?
Yeah, you're right. We didn't meet on Tuesday. You said we'll meet on Thursday, so
We didn't
I'm
meet,
just double checking.
wait, I thought I showed you the Newton's Law simulator on Tuesday.
Yeah, we did, but that was, okay, yeah, I guess, yeah, you're right. We
Yeah,
did meet on Tuesday, so we're not
yeah.
gonna meet on today.
I'll post an announcement. I apologize, I didn't do it ahead of time. I'm actually, yeah, I'm actually, I don't have anything new that I wanted to share with you in lab today, but I will be, I can always keep the link open.
If anybody has any questions or anything.
Yeah, I can make it a Q&A session, but I think for the most part, we took care of everything that we needed to take care of on Tuesday. Yeah, I was thinking that there was something else I wanted to talk to you about, but I don't think so.
Okay, yeah, I was double checking because that works out
Mhm.
perfect. So I got a midterm in a little
Okay.
bit that I gotta take, so I just wanted to double check to make sure. So,
Yeah, you're
thank,
good. I'll post an announcement, and then of course, you know that always, if you're having questions along the way, you can reach out to me, right?
yes, ma'am.
Okay. Well, that does it for us in this class today, and I'll post an announcement regarding lab shortly for those of you who are typically in lab with me. Okay,
Okay, thank you. You have a good day.
you do the same.